My name is Pranav Devalapalli, and this is my Physics 2212 Lab 2 report. The purpose of this lab was similar to that of Lab 1, where we take the tapes, charge them, and view their interactions. But in this case, we want to treat the tapes as distributed charges and not point charges. And we also want to create a computational model to estimate the force and charge on each tape. The fundamental concepts and models that were used for this experiment were the point charge force, or Coulomb's law, which is F equals K, Q1, Q2 for R squared, point charge field, whereas E equals KQ over R squared, Newton's second law, F equals ma, or mg in this case, g equals 9.81 meters per second squared. Fundamental constant k equals 9 times 10 to the ninth. The distributed charge model, which is simply a collection of point charges, and the concept of superposition, which is where we take the vectors of the point charges and put them together to get the vectors of the distributed charge. So a quick summary of the method and results is that we rip two pieces of tape, tape A and tape B, off of a base tape to charge them quickly, and we set them up as shown in the diagram to see how they interact. And the results were that they did repel, and Fg equals Fe equals approximately 2.06 times 10 to the negative third newtons. And we also approximately calculated that the charge on each tape is about 1.477 times 10 to the negative eighth coulomb. In the experiment, the system was the floating portion of the upper tape. The surroundings were the other U tape, tape A, and the supports holding tape B up. And the procedure was that we rip tape A and tape B off of a base tape to charge them, we arrange them as shown, and we view the interaction between the tape. To do this, we had to make some assumptions. We assumed that both U tapes have the same magnitude of charge. And we can make this assumption because both tapes were identical, the same length and the same material. We also had to assume that because they were subject to the same treatment, they had the same charge. Another assumption we made is that the mass of the tape is 1 gram per meter. And in this case, because it was 21 centimeters in length, we gave it 0.21 grams of mass. We also had to consider that the charge of the tape was equally distributed. It may not be, but we made that assumption anyway. And also we had to assume that only gravity and charge forces exist on the system. The results were that the inversion of tape B happened at a distance of 3 centimeters, even though there was initial movement at 8 centimeters. And the tape flips due to the external force because opposite charges attract, but like charges repel. This was my glow script code for the computational model. This section in the first image here is what defines the electric field. This section here defines the line charge as a bunch of point charges. And the entire left section is what creates the magnitudes of the forces, the net electric force and the net gravity force. And it also creates the arrows for the diagram. And the final section here with the print statements is what shows all the values. So here were the results of the glow script code. On the left, we have what was the original code that uses the point charge. And on the right, we have when we use the derived equation in order to get the magnitude of the electric force. And as you can see, on the left side, the magnitude of the electric force is a factor of 10 smaller than the magnitude of the gravitational force, when they should theoretically be equal. And so when we use the derived equation, which you can see on the top right corner, you can see that the electric force of 1.94 times 10 to the negative third is much closer to the gravity force of 2.06 times 10 to the negative third. We also got a more accurate Q value of 1.477 times 10 to the negative eighth, as opposed to 1.435 times 10 to the negative eighth from lab 1. We solved for this Q by taking the equation from before and rearranging it to isolate Q, and then plugging in the values as needed. And from that, we can get Q equals 1.477 times 10 to the negative eighth. From a little bit of trial and error in the code so that we can get the gravitational force and the electric force exactly equal and not just close to each other, we got that if Q equals 1.477376 times 10 to the negative eighth, that is the exact value. So that Fe equals Fg. So to compare the models, the point charge model was shown to be much less accurate. When using the derived equation, Fe and Fg were much closer in magnitude, as it should be since they are in equilibrium. And so that means the forces in the upward direction should be equal to the forces in the downward direction. It's still not perfect, because they're not exactly equal to each other. And this is because theoretically, a line charge is an infinite number of point charges, but here we used a finite number to represent the charge distribution. Some sources of error include our assumptions from before, namely that we assumed that both U tapes have the same charge, and that we had to estimate the mass of them. Also, different ripping speeds and our hands handling the tapes could have also caused variations in the charges. And the charges may not be evenly distributed, like we had to assume. So what if we had modeled each of our tapes as a single point charge, like in the previous lab? Well, if we modeled each of our tapes as a single point charge, as the experiment demonstrated, the result will be much less accurate representation of the charges. And these estimates differ because a line charge value is more likely to be closer to a real thing than the point charge because it's more representative of the true state of the tape. The tape is not a point, and so the charge shouldn't be considered a point charge. The distributed charge is more accurate to real life, and so its model will have a more accurate estimate. Thank you.